So when we graph quadratic equations and we are solving by graphing, there's 4 different scenarios that could possibly happen. So the first one would be that we get 2 real roots. So let's see how that plays out and what the graph looks like to give us that situation. Okay, so when we start to graph a function, the very first thing we're going to do is start with the AOS. So remember, we use that formula that's written in red to begin and start with our axis of symmetry. So the opposite of b is going to be -6, and my a value is 1. Okay, remember, it's ax squared plus bx plus c, and we're making sure that all of our terms are on the same side of the equation before we begin. Okay, which they currently are because this equation is set equal to 0. So I'm going to set up my axis of symmetry. -6 over 2 times 1 gives me -3. So when I properly state my final answer for the axis of symmetry, I'm saying x equals -3 because that is a vertical line equation. The axis of symmetry then carries into step 2 of finding the vertex, because remember, the axis of symmetry intersects the parabola at the vertex, so they share the same x value. So in order to find the entire vertex, we take -3 and we plug that into the function for x. Evaluating that, I get -1, but we have to state the vertex properly. The vertex is an ordered pair, so it's -3, -1. When we build our table of values, the vertex goes in the middle, okay? And we've already done the work for that in step 2. The other x values that I'm going to use are going to go up 2 and down 2 off of the -3 in the vertex. Okay, so -4 and -5 are going down, and -2 and -1 are going up. It doesn't matter which direction the numbers go in your table. You could have put -4 and -5 on top. You just want to make sure that the numbers are in numerical order. So we're now going to plug each of those x values into our function, and we're going to get out the y. We're creating a table of values that we already know how to do. We're just choosing our x's differently. Okay, so when I evaluate each one of those, you see that there is a pattern in the y values. That is your built-in check. So you know that you've got the correct vertex and the correct table of values if you get a pattern out in your y's. But don't just evaluate -1 and -2 and then copy those values for -4 and -5. You want to actually work them out to make sure that you're getting the correct values and that your pattern is true. Okay, so we're going to now put the axis of symmetry and the ordered pairs on our graph. So the axis of symmetry goes down as a dotted line, and then you plot your 5 points. Okay, when you connect them, you want to make sure that it's in the shape of a parabola, so the bottom is nice and curved. We're not making this pointy. All right, and now we want to state the roots. So the roots happen where the graph crosses the x-axis. Okay, and this situation says that we should be getting 2 real roots. So that means we're crossing at 2 different points. Okay, the roots are x values, so they need to be stated as x equals. So this parabola crosses the x-axis at -2 and -4. So my roots are x equals -2 and x equals -4. The only other thing that we would need to identify here would be if there's a minimum or a maximum. So does this parabola have a highest or a lowest point? It has a lowest, okay? There is nothing below the vertex here. It has a bottom. So it's a minimum, and we state the y value. So the minimum is at y equals -1. So we have to be really formal with the way that we state all of our final answers and the components to a parabola. So exactly as you see them here is how you want to be stating them in all of your work. So this was 2 real roots. Let's take a look at the second scenario. So the second scenario is 1 real root. So now that you've seen 2 real roots, think about what could 1 real root possibly look like. Okay, so take a moment and pause your video and write down a guess, okay, for this example of what the graph of 1 real root will look like. Okay, so the process of graphing always starts with axis of symmetry. And to get the axis of symmetry, we have to start off with our formula. So the opposite of b here is going to be -8. My a value is -1. That's a -1 coefficient on my quadratic term. So when I set up my axis of symmetry, -8 over 2 times -1 is +4. So formally stating my AOS is x equals 4. Okay, the AOS leads us into our vertex. So remember, they share the x value. So we're going to plug 4 into the function in order to solve for our vertex now. We get 0. The vertex is an ordered pair, however. 4, 0. Okay, AOS is a vertical line. Vertex is an ordered pair. To create our table of values, vertex goes in the middle, and we're going to go up 2 and down 2. So take a moment and see if you could fill in those x values before they show up. So we're going to go 5, 6, and 3, 2. So we're plugging in all these x values into our function. I want you to pay attention to how they are evaluated this time. That -1 coefficient on the quadratic term stays outside the parentheses, and we do order of operations. So we're going to do 2 squared first and then multiply by -1. Very important, because otherwise you're not going to get the correct y values and you won't see that pattern. Make sure you're evaluating all 4 of those additional points. Okay, so my axis of symmetry goes on my graph and my points come in. Now, before I bring up the other points, I can see from my function I have a -a value. It's -x squared. That means that my parabola should open down. So when you plot your points, you want to make sure that it's set up correctly and that you actually have a down opening parabola. If not, chances are that you messed up your sign somewhere evaluating in your table. So as my points come together here, I can see that this parabola is going to open down. And I'm going to state my roots, or in this case, it's 1 real root. So if you hypothesized correctly, 1 real root happens when the graph only crosses the x-axis once. And the only way for that to happen is if the vertex is on the x-axis. It doesn't necessarily have to open down. Okay, it could open up, but the vertex has to be the only point that touches. So the 0, the root here, is x equals 4. And now we want to identify, is there a minimum or a maximum? So is there a highest or a lowest point to this parabola? There's a highest point. Okay, since it opens down, the vertex is at the top of the graph. So there's a maximum at y equals 0. Remember, the maximum comes from the y value of the vertex. So this is scenario number 2, getting 1 real root. So the graph crosses the x-axis once. Hey, scenario 3 says no real roots. Well, having seen 2 and 1 real roots, make a guess about what no real root graph would look like. Okay, so I'm looking at the function x squared equals -5. I cannot start off the way that this is written. all of my terms have to be on the same side, which means I need to add 5 here to the other side of the equation. So I'm actually using x squared plus 5 equals 0. So my a value is 1. I have no b value, so my b value is 0, and c is going to be positive 5. So when I'm setting up for my axis of symmetry, I now have 0 over 2. Opposite of b is just 0. My a value is 1. Okay, so x equals 0 is my AOS. 0 is an okay answer to have for that. So I'm now going to take that, and remember, it's going to track into our vertex. So I'm going to evaluate the function at x equals 0. It means I'm going to plug it in. So x squared plus 5, plugging in 0, that equals 5. So my vertex is an ordered pair of 0, 5. Okay, so that goes in the middle of our table, just like we've been doing. And now we're going to go up to and down to for my other x values. So we're back to our tried and true -2 to +2 here. And we're going to evaluate all of those in x squared plus 5. Now, if you noticed in the last 2 examples, the zeros, or the roots, happened at the x values where they had 0 in the y of the ordered pair. I'm looking at this table, and this table doesn't have any zeros for the y values. Okay, so this is all starting to kind of come together, the fact that there are not going to be any real roots. And there's no zeros in the y values of the table. Okay, so we put down our axis of symmetry, and we plot our points and give a parabola. So why is this no real roots? This is no real roots because the parabola begins above the x-axis and then continues to extend upwards. It opens up. It's a positive parabola. So this graph is never going to come back down and cross the x-axis, and that's the only way that we can get a root, is if it crosses the x-axis. So that's how we have no real roots. So for the current moment and the knowledge that we have, that's where we're going to leave the answer for scenario 3 of no real roots. Okay, there is technically more that we can say about that, and we're going to learn that in the coming sections. Our fourth and final scenario. Oh, before we get to that, sorry, we want to do the minimum. So this has a minimum, okay, because the parabola opens up, and that happens at y equals 5. Okay, so the minimum maximum is always the y value of the vertex. So in step 2, that value that you get before you write it out as an ordered pair, that is where what we're taking from to give our minimum or our maximum. Okay, scenario number 4 now is 2 estimated roots. Okay, so estimating means they're not exact. So kind of try and think of a guess. What does that mean for the graph? All right, so again, this equation does not have all of the terms on the same side. It is not equal to 0. So we need to subtract 1 to the left side of the equation. That means that our c value is going to be minus when we go to evaluate. Okay, so my axis of symmetry is going to be -3 over 2 times 1. And since that divides out evenly, I'm comfortable with giving a decimal, so I'm saying -1.5. Now, we have not had an example yet where our axis of symmetry was a decimal. Okay, so this is we're going to treat this a little bit differently when we get to our table. For right now, for the AOS and the vertex though, everything remains the same. So I now take my AOS of negative 1.5 and I'm going to plug that into the function for my vertex. Okay, so we plug that in. See that we have that negative 1 on the left side of the equation now. And we're evaluating and get negative 3.25. Okay, so my vertex is all decimals here. So I'm going to go ahead and put that in my table. Again, just like normal. But now when I build out the rest of my x values, I don't really want to use decimals for all of those other ones. And if I went up 1, down 1, or up 2, down 2, I would have decimal values. So instead, on either side of the vertex, when your vertex is a decimal, you can go to the nearest whole number. So when I make this larger, when I make this smaller, okay, I'm going to go negative 2 and negative 3 on the low end, because those are the nearest whole numbers that are less. And then we're going to go negative 1 and 0, okay, because negative 1 is the closest whole number that is larger than my axis of symmetry. So now at least my other x values for my table, I don't have to deal with decimals the whole time. All right, so that's how we want to handle a decimal axis of symmetry. So I would definitely put a star next to this example and write decimal axis of symmetry, because you will see this in the future and you want to know how to handle the table. Once you do that, we're evaluating all the same. We plug in our x values into the function and we're going to get out our y's, and you'll still have a pattern when you do that. They'll just be nice numbers now instead of decimals. So we'll plot down our axis of symmetry on the graph, okay? And since it's negative 1.5, you're going to put it in between negative 2 and negative 1. It does not have to be exact. The same thing when you plot down your vertex. Okay, your other points are nice though. They can go on the actual coordinate point. And we're going to build our parabola. Okay, so since it already came up, we'll talk about the minimum here. So this is a minimum graph. Because it's positive, it opens up. So your vertex is on the bottom, all right? And there are no points lower than your vertex. So the minimum here is negative 3.25. So now let's talk about how do we state the roots. So I see that it crosses the x-axis, but it doesn't cross at a whole number. See, it crosses in between the 0 and the 1 on the right, and it crosses in between the negative 3 and the negative 4, but I can't tell just by the graph that it's perfectly in between, that it's at 0.5, and there's no way for me at the current moment to figure out what the exact decimal would be in between those values. So instead, when I state the roots here, I'm still going to use x equals, so we have to be formal in the way that we state the final answer, but I'm going to tell what two whole numbers it's in between instead. So x is between 0 and 1, x is between negative 3 and negative 4. And I can see from my table, I don't have any 0 y values. Okay, now in the previous example, it didn't cross the x-axis at all, and I didn't see any 0 y values. But now in this one, having the graph to refer to and looking at the table with no 0 y values, I know that it's not a whole number that's in my table. Okay, it's going to be some decimal value, and right now I don't have any further skills to figure it out. Okay, so for the time being, this is an acceptable answer where you state the two whole numbers that it's in between. Okay, so again, we have 4 scenarios: 2 real roots, 1 real root, no real roots, and 2 estimated roots. Okay, so this is the process for graphing and solve by graphing quadratics. Okay, very important. This is the basics and the foundation for the quadratic unit. So you want to make sure that your notes are complete and you have all 4 of these graphs and the definitions of all of the characteristics that we went over today. If you have any questions, please make sure those are included in your notes as well. Okay, thank you so much for watching, guys, and I will see you next class.